Today, we are diving into a really powerful tool from linear algebra, the Gram-Schmith process. You can think of it as a recipe for taking a set of vectors that are, well, a little disorganized and turning them into a perfectly neat, super useful new set. So let's jump right in.
And here it is. This is our mission. This problem, straight out of a textbook, gives us three vectors, v1, v2, and v3. Our job is to use the Gram-Schmith process to transform them into something way more useful.
But that begs the question, right? Why even bother? What's so great about an orthonormal basis that makes it worth doing all this math? Well, as you're about to see, the answer is that it makes a whole lot of really complex problems shockingly simple. So here's our game plan for today. First, we'll define our mission. Then we'll get our key terms straight. After that, we'll look at the blueprint for the process itself. We'll actually execute that plan to solve our problem, and then we'll wrap up with why any of this really matters.
All right, first up, the mission. We are taking a standard set of vectors, which is called a basis, and turning it into the absolute gold standard, an orthonormal basis. It's really all about creating order out of a little bit of chaos.
And here's a great way to think about it. Imagine you have a bunch of directions that are all pointing at kind of weird angles. What we're doing here is essentially straightening them all out, so they behave just like the simple, perfect x, y, and z axes we all learned about, where each axis is at a perfect 90-degree angle to the others, and each one has a standard length. That's the goal.
Now, to pull this off, we need the right tools. And that means we've got to get a handle on the two words that actually make up the term orthonormal. Okay, first, orthogonal. I know, it's a fancy word, but it just means perpendicular. That's it. If two vectors are orthogonal, they make a perfect 90-degree angle. And in the language of linear algebra, that means their dot product, which is just a way of multiplying vectors, is 0. Simple as that. And the normal part? Well, that just refers to a vector that's been normalized. All that means is its length, or its magnitude, is exactly 1. We call this a unit vector. It's like our standard 1-unit-long measuring stick. So let's put it all together. An orthogonal basis is a set where all the vectors are perpendicular to each other. Pretty good. But an orthonormal basis, which is our ultimate goal, is even better. Not only are all the vectors perpendicular, but every single one of them also has a length of exactly 1. It's the absolute peak of organization. Okay, so we know what we want to build. Now, how do we actually build it? Well, we use the Gram-Schmith process. This is our blueprint, the step-by-step instructions we're going to follow.
So the way this works is we just tackle one vector at a time. First, we'll take our original vector v1 and use it to create our first new vector u1. Then we'll use that new u1 to help us create u2. And finally, we'll use both u1 and u2 to create our final vector u3. See? It just builds on itself, step by step.
All right, enough theory. It's time to get our hands dirty and actually execute the mission. We're going to apply our Gram-Schmith blueprint to the vectors from that problem we saw at the beginning.
Okay, let's start with step 1. We need to find our first orthonormal vector u1, using our first original vector vol1, which is 2, 0, 1. And luckily for us, the first step is always the easiest one.
All we have to do is make it normal, give it a length of 1. We do that by just dividing the vector by its own magnitude. Now, the magnitude of 2, 0, 1 happens to be the square root of 5. So u1 is just our original vector divided by the square root of 5. Easy. 1 down, 2 to go.
All right, on to step 2, using our second vector, v2, which is 1, 1, 0. Now, this is where the orthogonal part really kicks in. We can't just normalize v2. First, we have to make sure it's perpendicular to the u1 we just found. So check out this two-part formula. First, we take our vector v2 and we subtract its shadow, or its projection, onto u1. Think of it like this. The projection is the piece of v2 that's already pointing in the same direction as u1. So if we get rid of that piece, what's left over, this new vector w2, has to be perfectly orthogonal. It's a neat trick. Once we have that, we just do what we did before. Normalize it by dividing by its magnitude, and that gives us our final u2. You're probably seeing the pattern by now, right? For our last step, we take our final original vector, v3, which is 0, 1, 1, and this time we need to make it orthogonal to both of the new vectors we've already made, u1 and u2. And this is where you really see how cool the process is. The formula just expands. We take v3, and now we subtract two shadows, its projection on u1 and its projection on u2.
What's left over, this new W3, is guaranteed to be orthogonal to both of them. Then we do one last normalization, and boom, there's our U3.
And just like that, mission accomplished. We followed the blueprint, and we successfully transformed our original basis. So let's just take a quick step back and look at what we did, and talk about why it's so important.
So look at this. On the left, you've got our original vectors, kind of all over the place, right? And on the right, you have our beautiful new orthonormal basis. Every single vector on the right is perfectly perpendicular to the others, and every single one has a length of exactly 1. It's just a clean, predictable, and really powerful system.
So what should you take away from this? First, Gram-Schmith is just a recipe. It's reliable, and you can follow it every single time to create order from chaos. Second, it gives you this much nicer orthonormal basis. But most importantly, these bases aren't just pretty. They make calculations way, way simpler. Think about 3D graphics. Using an orthonormal basis can make rotating a complex object as simple as a basic multiplication. That saves a ton of computing power, and it's why this stuff is used in everything from data science to quantum mechanics.
So, okay, you get the process now. You've seen how it works. The real question is, what can you do with this power? How could a tool that creates perfect perpendicular building blocks be used to, say, pull a clean audio signal out of a bunch of noise? Or how could it be used to calculate exactly how light should bounce around to create realistic shadows in a video game? The applications are out there, just waiting to be built.